All right, so we can learn what we used about the end behavior for power functions to do the same thing basically for polynomials. This is called the leading term test. So if the leading term of a polynomial function is an even power, because remember that these were positive integer powers. So if it's an even power, then both ends of the graph will go in the same direction as we go off towards infinity. If the leading term is an odd power, then the ends of the graph go in opposite directions. So pretty easy to remember here. So what I remember for these guys is I remember just what x squared looks like, right? Which looks like that. So this is y equals x squared. And we know if it's a negative out front of that, it's going to reflect down, right? And then I remember what y equals x cubed looks like, which is kind of like that S, sort of an S shape. And that way you can know without even having to graph it what your end behavior is. Okay, so here's some matching here. We're going to do this without graphing it at all. So we're going to look at our highest powers, right? Our highest powers on each one of these, thankfully, are the first terms in each of them. So we know the first two terms are even powers, and the second two terms are odd. So we know our evens have to go in the same direction, right? So that means that we know that this upper left one has to be an even power, and this lower right one has to be an even power. How are we going to tell which one is which? Well, we're going to look at the coefficient, the leading coefficient. And so for the x to the sixth, that's negative. That means our graph is going to be reflected downward. And that tells us that it is this one on the lower right, that this is f of x. And by process of elimination, that other one, the g of x, has to be the one in the upper left, but because it's also going up, right? All right. Now, we know the second two, h and k, are both odd, so we know that this one, that means that the endpoints have to go in opposite directions. So this one also has to be odd. And kind of the same story here, our h of x equals x to the fifth plus blah, blah, should look like our standard, at least at the end points, at the end behavior, should look like our regular old x cubed, which is this one. Right? So this one has got to be h of x. And this other one here has been reflected, right? Our endpoints are going in the opposite directions from the standard y equals x cubed. So this one has to be k of x. So we didn't even have to graph anything because this is matching. We know that we're good there. Okay. So let's see. We can talk about turning points and then we'll do some examples in the next video. So a polynomial of degree n, so that's whatever the highest power is, right, has at most n zeros and distinct zeros, okay? It could have less, okay? If that happens, that means some of those zeros are technically repeated roots. So a turning point in the graph is going to be a point where the graph changes direction from increasing to decreasing. So for instance, if we had this, we would have 3 zeros, 1, 2, 3. This is a cubic. And we have 2 turning points. One here where we go from increasing to decreasing, and one here where we go from decreasing to increasing. All right. So this one, so the turning point is, okay, so we said that, and that at most, a graph would have n minus 1 turning points. I don't know why that's not here. Okay, so if we have the graph, so we have the function, the polynomial, f of x equals negative 2x to the fourth minus 3x to the third plus x minus 1. The maximum number of possible zeros, well, it's going to be equal to the degree of the polynomial, 4. And the maximum number of possible turning points, 4 minus 1, so 3. So we might expect that this graph, we might expect that it looks kind of like that. We won't know till we graph it. And why did I make this pointing downwards and both ends going to the same direction? Because it is an even power. And our leading coefficient is negative, so it's been reflected. So our end behavior, we're going to write this as x goes to negative infinity, f of x or y goes to, let's see, as we go this way, we're going down, so f of x is going to negative infinity. And as x goes to positive infinity, f of x is also still going down, still going to negative infinity. So as we go this way, we're going down. So there we go, we have our sketch, and we're going to do a few more examples, and that's going to wrap up this section.